We're going to go ahead and get started, folks. Thank you for coming. My name is John, otherwise known as J.R. Rath. I work with Christine Hoffer to try and support you folks on every day of the year. This is the design track, so hopefully some people here are interested in the CEU credits. Can I see a show of hands of people that have registered for them? Terrific. If you haven't been here before, I'll just repeat. At the end of the session, come on up to this table. I have a sheet that you need to sign. Just need to sign once if you're already pre-registered. If you didn't get a chance to pre-register, come on up anyway. I've got another sheet, and we'll take care of that to make sure you get your CEUs. So thanks again. I also get to introduce Joe Pejsa, who's our speaker today, and he's going to talk about all things, as you can tell, fault or not fault. You know, he's one of those guys that must have a super interesting job. I think he probably could tell you as much about discount plane tickets or air travel as he could geothermal, because he's got a service territory that covers Canada and the United States, right? It's just a small territory. I'm guessing you're on the road a fair amount.
Yeah, a fair amount, yep.
Yeah, for sure. But in terms of his background, he has lots of work and expertise in geothermal well fields. He does estimates, and he does a lot of technical sales. He's also a longtime ICHPA supporter, so if Jeff Hammond's in here, Jeff, you got a super supporter here. Please help me welcome Joe Pejsa.
Thank you. I just want to make sure that I'm saying that talking to this right. Everybody can hear me? All right. If I get quiet, just Stuart, give me a nod. So I recognize some faces. I've been doing this for about 20 years. I started out at GHP Systems and went to ISCO, and I'll talk more about that as I go through the presentation. I get a lot of, you know, the topic is to vault or to not to vault. It's probably like, I don't know, it's kind of misleading because it's such a hard question, and there's so many different answers to the question. So we'll get started. If you have a question, you can raise your hand during the presentation, and JR will come give you a microphone so that you can ask that question. If you want to wait till the end, I'm also going to do it at the end and open it up for questions. It'll probably be, it's a one single topic, so there's not a lot to talk about. So it's going to be, the more you guys participate, the better this is going to be and the longer it's going to go. So it's like I said, it's a pretty simple topic, but yet it can be very complicated too. Like JR said, my name is Joe Pejsa. I work for Infra Limited. Been doing this for about 10 years, and I sell through the United States and Canada exclusively geothermal vaults. I used to do a lot more other things, you know, other products in the geothermal well field business, but I just do vaults now. So we're going to talk a little bit about the vaults, what they are, what they do, how they work, what they're made out of. Here's my introduction. Got a little ahead of myself. I've worked for Infra Pipe. It used to be Uponor, and formerly before that it was KWH Pipe. I spent 5 or 6 years at ISCO and about 4 or 5 years at GHP Systems. I have 20 years experience in the ground source heat pump industry, and I focus mainly on well fields, well field design, geothermal vaults. I don't do, once you go inside the building, you lose me pretty quick. So some people say I'm an expert in well fields, but I kind of know how they work, and then if I don't have the answer, I'll find the answer for you. So if you have any, and if there's a question that I don't have an answer to, I can see several faces in this room that I know might have the answer. So what is a geothermal vault? It's an underground structure for locating the central manifold on a ground source heat pump project. It's kind of like the radiator to the car. it's something to bring this system together and then run it into a building with 2 lines instead of multiple lines. So on this particular picture here, this is a vault that was delivered to Princeton, New Jersey. We'll talk a little bit about this design later on, the complications that were there, why it was, what things need to be changed, how you can make it more efficient. I'll talk about efficiencies too, and how to make better vault designs. Okay, what type of vaults are there? We typically see 2 vaults in this industry. We see a lot of HDPE vaults. I don't see as many concrete vaults as I used to. We see more HDPE now because there are multiple manufacturers out there. The concrete vaults, they have some issues with leaking, cracking, other issues and they're heavy, so sometimes you have to do things on site. So if you look at the one on the left, or the picture on the left there, it was just a cylinder. They wanted to try to get the manifold inside of it. I believe ISCO built this years ago when I was there. Built the manifold to fit inside the round cylinder. On the one on the right, it's one of our vaults, and you can see that we do a gray color to keep it light inside, and you can see on this one in particular, there's no balancing valves in here. It's all HDPE cylinder. They run in 72, 84, 108, 120. Different sizes are available and different size mains. We personally we can do up to 20 inch. That's as big as we've done. Like I said, this is going to go pretty quick. Some of the vault components, there's multiple things that can go inside of a vault, but we try to limit it because that's where the issues come in. The more stuff you put in them, the worse it gets. So try to keep it simple. So you have electric lights, outlets. You can have a sump pump with or without a pit, or without a sump pit with or without a pump. Ventilation, the OSHA ladder, and that's regulated by OSHA, not by us. I mean, it has to be so far from the lip when you jump in. It has to be so far from the bottom when you're at the bottom. The spacing has to be 1 foot spacing. There's certain guidelines that OSHA guides, and so you have to put an OSHA ladder in there. Slip resistant graded floor. I would say out of all the vaults that I've done, maybe only 5% of them have slip floors in them. It's a little dish at the bottom, but it's pretty flat when you start and get into 120 inch pipe, 84 inch pipe. So there's some need for it, but most of the time it's not put in there. 2 manways. See a little bit of, we see, I don't know, probably 25% have 2 manways, and I think the biggest benefit of that is the manways are restricted to usually 28, 30, or 36 inches. You start to put in a 8-inch hose for flushing and purging, 2 of them, and you can start to see it gets a little bit crowded going up and down the ladder. So the second manway is really good for flushing and purging and pointing those fill ports up to that so they can connect to them from the top, and then be able to access everything, open and shut all your valves on the purging side. So you don't, when you're climbing in and out, you can easily get in and out. I think when I look at a vault, I don't know, I've probably been involved with over 1,000 vault sales in 20 years, and this particular project was quite insane, but a very good example of how to keep it simple. You want to put as many bores together as you can before you go to the vault. And the reason for this is because of the cost. So on this particular vault, in this particular project, I'll show you another, we can go to the next picture. So there was 100 slinkies. They were 1 inch. And you could probably put it in one vault, but there was 5 vaults on this project, and the total cost was about $300,000. So on top of that, if you look at these circuits, you can see that they have a pressure gauge on the supply and the return on every circuit. They have, it's 1 inch, so it's all threaded. They don't make a flange connection. They have air release valves on every circuit, supply and return. If it's a pressure system and you flush and purge it properly, you know, there's just, I think I totaled it up, there was 1,254 threaded connections underground. And it's just, so this is a prime example of trying to keep it simple and try to limit the number of circuits that you have underground. And as I go on down the speech here, I've probably talked myself out of more vaults than I've ever built. And the reason why is, this is an example right here. This was a home. It was a huge home. But I could have done this on a 6-inch made with 3 4-inch circuits, put it in the basement, charged him $10,000. He could have bought me a Ferrari, and I still could have given him $150,000 back. So, I mean, and the homeowner, he didn't know. Like, he just trusted the engineer, that the engineer was doing the right thing. So, and maybe he did know, but it's a perfect example of, you know, we need to keep it simple, keep it basic, try to put as many fusions in the ground as possible before you go in the vault. And some of that is, there are some engineers or some designers that think that they don't want any fusions in the field. That fusion is a lot more trustworthy than any kind of threaded connection over the next 5-10 years. You know, some of the guys that have been installed these, like Tony and stuff, you guys are just shaking your heads, and you agree. I mean, it's, you know, try to limit the complexity of it all. Something, yeah, so I already touched on the cost. It's extremely high. No internal heaters. You know, this guy wanted they wanted to put heaters in these. It was in Florida, so I'm not sure what the heater was for. Ventilation fans, and they need to be stored inside in a maintenance room. There was a manufacturer, he's out of business now, but not that that's relative, but they put the ventilation fan inside the vault. And I don't know how many people deal with confined space, but I deal with it a lot because this is what I do for a living. And especially on military bases, you learn a few things on a military base real quick. The OSHA states that you cannot draw air into a confined space. So if the fan is inside the confined space, it's drawing air into it and through the fan and then back out. So you're creating a suction. So what it states is you have to have positive air pressure inside the vault. So that means that the ventilation fan needs to be outside the vault, not inside the vault. And so you could store it in there. That'll go down, when we get further down, we'll talk more about that. But you can store it in there, but again, there's other issues that come with that. You want to create a positive pressure. So if you ever looked at somebody that's working in the street, they got the ventilation fan sitting outside, and when they get inside, I don't know if you've ever seen this, but when you get inside of a confined space, you'll see wind, you know, coming up. It's because that positive pressure is in there, causing that airflow to bring the contaminants out of the confined space and blow them into the atmosphere. So that's why and it has to be in a safe location, away from the car, and, you know, away from generators, away from different contaminants that can draw it into that space. So again, there's the job. Okay, some of the topics for discussion. You know, where's the location of the geothermal vault? Is it underneath the parking lot? Is it underneath, you know, where is it at? I'll go into more of all those locations as we get further down the discussion here. You know, is there an issue with the water table? You know, what's the water table? Is it 10 feet, 2 feet, 5 feet, 1 foot? You know, anybody that's been in this industry knows that if it's 3 feet, that's a problem even for tying the header in, let alone the vault itself. You know, what are the savings? Are we doing the right thing? Are we saving a lot of money? Are we spending a lot of money? Is it worth the money that we're spending? You know, what's the expense? And then, does it need to be H20 rated? HDPE vaults are H20 rated. A lot of guys will say that they're not, but it is. There are certain vaults out there that are made with some sheet stock and other stuff. They are not H20 rated because sheet stock is not a structural material. The cylinder vaults are H20 rated, and they can be H20 rated once they reach certain depths. I'll go into that as we go down the presentation here. So I get a lot of calls from engineers asking me what, it's how can I determine if a vault is needed or not? And I think that ultimately the answer to that question is it just depends. Like every project is different. Is it a new build? Is there lots of room? Is there an existing building? Is it an existing building with a boiler room? Existing building with a ton of utilities around that room, around that building, downtown somewhere? What's the location of the well field, the distance to the building? Those are a lot of the key questions that I'll ask engineers when they're talking to me about vaults and what I think or what my opinion is on if they need a vault or not. So some of the locations that you'll find for a vault, you got parking lots, you got grassy fields, athletic fields. A lot of geothermal well fields go underneath football fields. Seems to be a lot of that do. It just seems to be the location. Baseball fields in Princeton, and then parking lots are probably the second biggest location. Don't see very many in grassy fields unless it's a college or campus or something like that. And then you'll see some grassy fields, stuff like in those locations. This particular field here is a retrofit, and it was just picked. You can see the baseball fields kind of to the side there, but you can see there's just a grassy area out to the south of the building.
Can you point out the vault location there?
What's that?
Can you please point out where the vault is on that?
Okay. Do you want to come get the question, John? I'll just repeat the question. She wants me to point out where the vault is on this particular job. So on this one right here, the vault is right here. And on this particular job, this is something I'm going to talk about later. I'm going to talk about how you can make this one more efficient. But on this particular one, that's the vault location. They came out of this end and then tied it in this way. So they got the reverse return, coming out one side and the other of the vault. And then the two lines are running right up here, and they actually enter the building right up there. Did everybody get that? Okay. Hopefully I'll talk loud enough when I'm not, and I'm like. Okay, so here's an example of a football field. And I'm going to kind of skip back and forth. Now, my presentation is kind of a loose-knit one. Like I said, it's not a hugely interesting topic. I can see most people falling asleep. But this particular one was underneath a football field, and the vault is by the track. Okay, this was the original design, and as we go through this, we'll come back and we'll visit this. But just be thinking about in your head, as a contractor, what would you do? As an engineer, what would you do? And then let's see if we can come up with a better solution for that vault location. Island parking lots, I'm all for it. Let's do it. That's the best location as far as I'm concerned. Because if there is an issue, we're not digging up the whole parking lot to get at this vault. And most of the time, that manway lid is in the island itself. So we can put a light duty cover over top of it. We can use the cover that comes with the lid or with the vault. It's the best location just because it's versatile. I had a job in Ohio where they put the vault in right in front of the garbage truck, or before the garbage, and we had H20 lids in there. We used H20 rated lids. They were aluminum lids, and I'm not going to say the manufacturer because it didn't matter. So what happened is the garbage truck would pull in, and he would literally stop right on top of the lid, back up across the lid, and so about every couple months they were replacing the lid. Finally, they went with a sewer lid, which was a better style lid, but the location of the vault also could have been moved. From where they were at, there was some other issues on that site. It was in Berea, Ohio, and not but about 10, 15 feet away from the vault, there was an electric transformer right there. So it should have been moved anyway from that perspective. But the other perspective is they had the manway right in the middle of the path for one of the heaviest trucks that's going to come in to the parking lot. It was rated, they had it rated for cars. They didn't have it rated for the garbage truck. So here's a good example of a manifold and the kind of space that it might take. This vault is, or this manifold was at DMU. They did try to do a vault on this. They talked about a vault, but the cost was expensive, and the location was close enough to the building. They had the room, so there were 16-inch mains, and I think it was 48 4-inch circuits. I can't remember exactly. The picture on the right is actually a vault, but it's a built-in-place concrete vault. It was on a job in Wisconsin. I have a knack for remembering the jobs and not my name, so I can remember where all these are, but I have a hard time remembering other things. So this vault was in, this is a vault, but it's actually built attached to the building. So there's a doorway. You can see the pumps. The pumps are on the top of the drawing. There was a doorway, and they actually buried this structure and actually connected it to the building and made a separate little room off of the building to put this manifold inside. So it's technically a vault, but it's a manifold that's inside the building. So it's, you know, it was a unique design and a unique way of doing it. Here's another location for manifolds. And the reason why I'm bringing all these up is because just to talk about what's the difference is, what the locations are, and how come we should be doing it and what should we not be doing it. This was in a parking garage. This is on the Obama Museum. This is in the basement level. They're actually burying this whole parking garage is going to be about 10 feet below, buried in dirt, and then this manifold was below it. 10-inch mains, 17 4-inch circuits, no balancing valves. We'll get into balancing valves in a little bit. We'll jump back and forth and talk about that. Bypass. So it fit in this location. This was another project that we started as a vault and talked them out of it and told them to put it in here. So again, I've talked myself out of more vaults than I've put in the ground. So when we're talking about anti-flotation, water levels, making sure that vault doesn't float out of the ground. And yes, concrete vaults will float out of the ground. I've seen it happen. If they're not backfilled, if they're not anchored, if they're completely tight, they're going to float. But if they're not completely tight, then they won't float. So the concrete guys are all like, we won't float. Yeah, because water's flowing in. So we do the plastic. We test them to be leak-free. We've had leaks. I've had leaks. Not going to say we're 100%. I always tell people if there's a leak and I don't know about it, then I can't fix it. But if there's a leak and I know about it, we can fix it. We do the calculations to 1 foot. Sometimes we do it to ground level. Technically, it'd be nice if we knew what the actual water level is. We get some engineers that want stamped drawings, and they want a stamped drawing to 1 foot. But there's some risk of that on the engineer stamping the drawing. If the water table's at 15 foot, it's probably never going to see water. So it'd be better to design it a stamped drawing to what is the actual water level of the location. Our calculations are kind of based on spring line. We do go, like I said, to 1 foot, and then we can stamp them. We can have them stamped and sealed, and most manufacturers can. The big thing about anti-flotation, let me see where I'm at here. The big thing about anti-flotation is on a plastic vault, it's leak-free. This has happened in South Carolina. There was a hurricane coming in. They had the concrete on the ends. The vault was exposed, and they didn't have time to backfill it. So we told them to flood them because the weight of the water inside the vault will keep it in place. But if you let just the concrete out on the outside, that's not enough weight to keep that vault from floating. And the reason why is because when we do the calculations, it's based on the soil being backfilled around it. So the weight of the soil, the weight of the concrete are what holds that vault in place. So if you got a situation where you're not going to get it filled, and they're talking about 5 inches of rain and everything's coming to the well field, because as a driller, we know that well fields are in the lowest spot and all the water's coming to us, and we're going to sit in the mud for a while. So, you want to prepare for that, especially if you're tying in a system and you got just concrete on it. You either better backfill it quick and know that you're going to have to take that out, or go ahead and flood the vault. It's clear water, it's clean water, just flood it, pump it out the next day or whenever when you're ready for it, and continue your install. So let's look at designs. This is kind of a good one. The perfect example of a possibility of maybe a manifold inside. We got 6 circuits, 22 bores, or we got 6 circuits on this one. They're all 3-inch circuits. If we have 11 bores on a circuit, we're just over top of that 3-inch threshold. So why don't we jump it up, add some more bores to that design, make it 22. Depends on the flow. Some people argue maybe 3 inches too small, but let's just, for non-argument's sake, let's say 3 inches good. We take 3 circuits here, we put it inside of a little manifold, 6-inch circuits with 3-inch manifold, 3-inch circuits, 6-inch main, sorry. Now does it fit in the mechanical room? We're probably talking about something that's 4 feet long versus something that was probably, 7, 8 feet long. So when I design manifolds, if I look at a length, so if an engineer calls me, customer calls me, I don't have to go into anything really. I can tell you right off the bat what it's going to be approximately. If you got a 6-inch main with 10 3-inch circuits and it's 2-sided, that's 5 on each side. Your spacing is typically 1 foot, you add a half foot, so it's 5 plus 3 in the front plus maybe 2 in the back. You're looking at anywhere from 7 to 10 feet, most likely 9 to 10 feet long. If it's one-sided, you got 10 circuits, you got 9 plus a half. You're at 10 feet plus a couple on the back plus a couple on the front. You're probably looking at a 14, 15-foot vault. It's pretty easy to come up with those numbers just based on what you standardize for your install and for the manufacturer guys making the manufactured vault. So any questions so far?
With the leak-free vault, how are you sealing the pipe penetrations coming in and out of the HDPE?
Yep, I will. I'll repeat all of these, John. Okay, so the question is with an HDPE vault, how do we seal the penetrations coming in and out of the vault? So let's talk about concrete first. Concrete's going to be a core hole, and they're going to link seal it and pinch it. Problem with link seals and everything over time is pressure from the outside as the ground settles. If you don't go inside that vault and fix those link seals on a pretty regular basis in the beginning of the install, water's going to leak in there. So on a HDPE vault, what we're doing is we're using a method called extrusion welding, and it's actually just very similar to steel welding, where it's 500 degrees of a blower, blowing 500 degrees with what they call an HDPE rod. It comes on a reel, and that you rough up with material, usually using 24 or 36 grit sandpaper. You rough up your edges on your pipe and your housing. So maybe we can go back. So right here, so you're roughing up your edges around the housing, you're roughing up your edges around the pipe, and all the components here, you can't really see it, but there's like a sheet stock top on here. Once you get it tacked together, then we call it, the feed rate is in pounds. So you might have 10 pounds an hour, 5 pounds an hour, and that welding machine will preheat to about 256 degrees. The blower is about 500, and as it extrudes out, it melts that plastic. The two form and melt together, and that's how we hold it together. Does that answer your question? It's a little bit hard to explain not having the machine here. It's really cool. Probably would add some time to my presentation, and really cool to do that kind of. It's cool to see it. I've been doing this for 20 years, and I still think it's kind of cool to weld with plastic versus steel. And it's amazing how durable it is. I've seen a lot of people run into these, and they hold together, which is, to me, just doesn't make logical sense. I'm an industrial engineer, so I'm a welder by trade. I welded for 10 years, steel welder, and then I went to school, industrial engineering, and that's kind of helps me with my welding background on some of this plastic welding.
I might have missed this in the beginning, but
I might have went too fast too. I don't know. She asked, what is the functionality of the vault? And I think what I said is like it's a radiator. So I should have probably clarified that. Let's say that you got a system that's 100 bores, and you have to team those bores up. That's what goes back to that residential where they had the 100 bores there, but they had them all tied in individually to a vault. So if there's 100 bores there, how do we want to pair those bores together? And once we pair them together, we have to run them into a manifold. So that manifold, whether it's in the vault or in the building, is what we're trying to, determine how that's going to be done. Does that answer your question? Or partly? Go ahead. So well, that's the magic question. That's the question that engineers. So she asked me, she said, so the decision to make a vault or not is based on what? Is it based on distance? I don't have that answer. And the reason why I say that is because every project is different. So when we go back and look at this, so existing buildings are hard because sometimes the utility rooms are smaller. And I might answer your question as I go down, but we'll kind of talk about it now. So the hardest question is it's based on every project is different. And the reason why that is because every project has its own unique footprint. So if there's an existing building, there might be limitations, to how you get that manifold. All those 100 bores, if they're tied together in groups of 10, that's 10 circuits that have to go in. Those 10 circuits are 20 lines. Those 20 lines have to go inside that building. If that building doesn't have enough room for 20 lines, and it's HDPE, so anybody that's worked with HDPE, we are limited. The distance between the circuits isn't like steel. You can't just put that thing 7 inches away from the other one, turn the butterfly valve so that they don't hit each other, and make it work. You got about a foot on some. So some of it's the minimum on 3 inches, 10 inches. The minimum on 4 inch, you should probably be 11 inches. Minimum on 2 inch is probably 8 inches apart. And then you're pushing the limit of the machines and the equipment and the time that it takes to build that stuff. So does that help you better? And I'll get into it more too. So
Joe, we've got a question back here, and also a time check. We're about 12, 15 minutes before wrapping up.
okay.
All right, hey Joe, this is Trey Austin with GEO
Yeah.
Energy Services. So to kind of help explain to her a little bit more, we're both an engineer and a contractor at the same time.
Yeah.
Usually the decision point, in our opinion, comes down to pressure drop. And what's the pressure drop of bringing all of the header circuits into the building in that distance versus putting a local vault outside closer to the field and then coming into the building with larger 4, 6, 8 inch mains that help reduce the pressure drop. Because this is a key factor in the design of the geothermal system that a lot of engineers overlook. You can have the greatest, most energy efficient geothermal heat pumps in the building, but if you don't size your hydronic piping system correctly, all of the pumping energy will eat all of the efficiency of the heat pump away. Yep. So really the decision on the design point is, what's the pressure drop in a scenario where you bring all the lines into the building, or what's the pressure drop when you put a vault outside and then bring in larger distribution circuits into the building? That's what it comes down to.
Yep.
And
Yeah,
then
so
one more comment too.
Go.
Also on the vaults in the building, everything that you've done has been great. The other thing that we do that can get overlooked is we make sure that there's always a bypass bridle inside the building. We call it an H bridle. It's basically 5 valves. It's 2 building side valves, 2 geo loop valves, and then 1 bypass in the middle where you could bypass the building, you can bypass the vault, but you have the flexibility. We've ran into a lot of situations where we had some issues, and if we didn't have that bridle to make those bypasses available to us, we wouldn't have been able to troubleshoot some issues that we were dealing with.
Yeah.
So I think it's key to make sure that the building side has that bridle. Even if you have isolation valves in the vault, you still want that bypass bridle in the building.
Yep.
And that's all. Thank you.
yeah, I agree. Trey 100% with the H bridle. The speech is about to do vault or not to vault, but there's a lot of things that go into it, like Trey just said. It's just like every job is unique, right? So, and we put bypasses. I know ISCO does, something that we did back, and everybody puts bypasses in vaults. There's only one manufacturer that doesn't right now, mostly on his coffin, more the sheet stock. The bypasses are in every vault because you can flush and purge from the building, or you can flush and purge from the vault, so you have some options. And so and the pressure drop, the header loss, the head loss, all that kind of calculation. I would love to go into all that stuff because that's the meat and potatoes of all this is, like you said, it's what's the pressure drop, how much pipe. If you're going 500 feet, and that's on this job here, on this particular vault, I'll get into this in a second. But Connor, did you have a question quick? Okay, I'll keep going, and then we'll finish up, and then we'll do questions at the end. That way, what do we got, 15 minutes? Okay, the rest of this is pretty quick. It's just talking about what Trey and so how far is the building? Is it 420? It's 420 feet on this one. Is it feasible to do an interior manifold? Probably not. It's 420 feet. 420 feet of 3-inch pipe. Well, now you're gonna have to upsize the 4-inch pipe, possibly 6, depending on your flow, and you got more volume. If you got glycol, you just added more expense. So there's variables that come into every project too. Okay, so you got 1,900 gallons in the 8-inch. You got 10,000 feet of 2-inch with 1,500 gallons. Labor to install all that pipe to the building. You can probably make this a little more efficient, double it up, and reduce the number of circuits. But another thing that I talk about we want to make 22 bores, but there's also a diversity factor here too. Like sometimes you don't want to lose 50% of your well field if one goes down, or even 33% of your well field, So, I'm saying like we could do 6-inch main with 3-inch circuits, but it's the same token. It might be better to have 4 circuits so you only lose 25% of your well field. If you're in the middle of winter in South Dakota and it breaks down, what are you going to do? You're not digging it up. It's 5 foot deep. It's 5 foot of frost and you're sucking the energy down, so the frost is all the way down. Look at the distance. Here's another one. This goes back to that one we talked about, that vault. So what on this one here, again, it was 650 feet to the building. It's probably a vault project. It's a long ways to that building. So go back here. So what we did here is, that's a terrible location for the vault because it's right by the track. And if you put an H20 lid on it, now you have a steel structure. Somebody falls and trips on the track and hits their head on the steel structure. Probably not going to happen, but it could happen. So what we did on this one is we moved it actually to the under the bleachers. We pushed it out a little bit. We put more 3-inch in the ground, moved the vault underneath that shaded area, and then put the vault underneath the bleachers, put an H20 lid on it. Nobody can get in it, and that was one thing that we did to improve that project. We still went with a vault because manifold was out of the question. It was too far to the building. This is the other one. So this is the same job. We did change this job from I think it was 18 circuits down to 14 circuits. We turned the well field and we did U-shape header on it. This is an existing building constraint. I keep bringing this one up because the building was a small boiler room and there wasn't enough room for the pumps and the manifold and everything inside. Again, diversity is here. You could have probably broke this down into 5 3-inch circuits instead of 10 2-inch circuits, but it might change the volume too, and the price went up because you had your volume changed on your 3-inch pipe. H20 load rated. It depends on the burial depth. So HDP vaults are H20 rated at a certain depth. The manway is not going to be H20 rated. It's plastic, so we need to make sure we protect that. We backfill. We do that right. But if you get to 30 inches below grade, then that vault is actually protected by the soil and the compaction above it. That's how we get the H20 rated. If it's shallow bury, you're going to have to put 18 inches or less. We'll put a concrete pad over top it to protect it. I got about 4 more slides, and then we'll do questions. This is our load calculator. We can actually calculate the load and what the strength of the pipe it is, and if it can take the load on an H20 calculation. So again, my summary is, how far is the loop field from the building? Are there any outside features, mechanical, any access to that mechanical room? Is there existing utilities? Is there a lot of sewer lines? If it's downtown and you can put it underneath the parking lot and you got to come across the street, you're not going to bring 20 lines in, you're going to bring in 2 lines. How much space is available inside the mechanical room? What's the volume of the fluid? Again, comes back to that running 44-inch lines in versus one 8-inch or 10-inch line. What do the economics look like? There's a lot of things to do with that. Sometimes vaults are really expensive, and it's like, holy crap, we could run those lines in, and it's cheaper. But if it's 400 feet away, it's probably not. So what's the water table? If it's a high water table, they're kind of hard to keep in place. You dewater them, get them filled in, get them properly installed, and you're good to go. And then what's the H20 requirement? So again, in summary, I think every project's unique because every project has its own challenges. I mean, Trey, Connor, other engineers in this room that I recognize, they all have their own challenges. And what's that head loss? What's the pressure? That kind of stuff comes into play. So, are there any questions? Kind of went through really quick there.
You've talked about the water table. What about systems that are being built in areas that are vulnerable to occasional and increasingly frequent flooding?
Yep. Yeah, we see that a lot so everybody heard the question about flooding? Okay, so, you do the calculations based on zero water. Once it's over top of it, then the water will hold, there's water pressure there also. Most of the time, if it gets to the lid, it's probably going to leak anyway, because the lid they are leak tight, but they're in and out of them. They're just not foolproof that way. The gasket doesn't get put in place. Something happens. I see a lot of leaks on builds that have leaks from the lid. So I wouldn't shy away from it. I see a lot of them in that flood zones. Connor, make JR work here.
Yeah, the great presentation, Joe. Just to touch on that lady's question, I think it would help a lot of folks in the room. And you were kind of doing this during the presentation, a little gut check, wow, this one's 400 feet away. Other than, if all of the other variables are the same, what is your gut check distance from, the well field to the mech room when you would consider a vault? 400 feet, 500 feet, 300 feet?
300.
I think that would help a lot of people in the room.
I think 200 to 300. I think that's my gut. Like, if it's 200 feet, yeah, it's getting out there a ways, If it's 50 feet, I'm looking at a reason to put it in the building. If it's 100 feet, I'm still kind of looking at it. It depends on the number of circuits. Trey, any thoughts? Yeah, I'd say 200 to 300 feet.
One more question here.
Bobby, with Watchtower. In a project where we have about 2 Costco-sized buildings with 300 wells under the foundation, the energy plant's about 150 feet away, would you look at putting vaults within the building footprint to access those, like multiple vaults? Because currently there's no access to the wellheads right now.
Okay, so go back to the Obama job. There was 170 wells on that job. 70 of them were underneath the footprint, and they brought them up through the floor to the manifold. So if there's room for a manifold, just bring it to that corner and manifold them underneath the floor and bring them up. But if there's not room, it's just all about if there's room. If it's a building that size, is it possible that we can bring them up through the floor and manifold it inside? Manifolding inside is going to be the best bet. It just adds life to your components,
Okay, I'm sure we can convince Joe to answer some more questions after the session, but for those of you, again, that need credits, please see me at the table over here. Can we have a round of applause for Joe? Thank you very much.
Thank you.